Draft physics video and such. So, yes, we'll get to some drawing probably, or something like that. Mostly on static electricity charge, and just going over some of the things that, yeah, I know that. What part I know is happening, and just see if I can seed some better understanding of combining all of the little things you have to combine. There's lots of little facts about electricity and magnetism, and it's putting them all together and then finding a model that fits all those circumstances. So that's what I've just been trying to do. It's sort of inspired, I suppose, this focus by Mindless Marbles. So just happened that it turned out that I started going the direction he was inquiring about without even, just whatever. So I'm wondering exactly how your model of static electricity, I assume that it deals with the accumulation of charge, right? And charge would just be electrons. So that's sort of the interesting thing here. Charge is either too many or too few electrons. And that collection of charge, electrons, would act like a filter. Well, clearly the electrons and the protons are the filters, so anytime you segregate them again, if you have too many of them in one end and too few at the other end, kind of a thing, that's going to be a dipole magnet. Is that the correct approach? Yeah. If that's the case, though, how would the comb make a difference compared to the magnet? Yeah, so I thought of that's what I had thought of, and then I said, wow, what I thought of sort of answers your question, because I was thinking about static charge. So I was thinking about you always got to separate conductors from non-conductors. So even if you spray paint a balloon with a metal, it becomes a conductor. It'll behave completely different than how it would behave if it was made out of rubber, because it can collect charge on a thin layer of it, a very undense charge. I mean, it can be a very high charge, very high voltage, but it has no amperage, it has no volume, because it's not storing charge, it's just storing electrons. So it's just a layer of magnetism, you could almost say, but it doesn't have any depth. But the question I was thinking about was how weak the attraction is, but it's not really weak. See, it's strong from a distance. It's almost like the inverse of a magnet, a charged balloon, let's say, with static electricity, and that it will seem to be quite attractive to things, grounded things, if it has a lot of electrons or very few electrons. But it doesn't seem to cling with any strength like a magnet, so it has no depth. But that's because it's the bonds of the electrons that are breaking. So in a traditional magnet, you're magnetizing, you're rearranging the position of electrons and protons into domains, and they're all pointing, in a certain way, so that it creates this filter. Everything going this way ends up coming out red, and everything going this way comes out black out of the bottom. And those electrons and protons can't go anywhere. They're can't break those bonds, because those bonds are strong chemical bonds. So it's really just about free electrons. So static electricity is all about free electrons and what they're doing. So when you peel the balloon off the wall, you're just essentially leaving the charge behind, usually. It really won't, you stick it once, you have to move it or change its position to stick it again, because you've essentially pulled the glue off when you removed it. Improbable. The electrons will go one or the other, but the point is the bond will be weak. One of the two sides, if not both of the bonds through the electrons, will be weak. So there won't be a strong bond on either one, which means the electron will break easily from one of the surfaces. So you're really not breaking the force. You're really not pulling the electrons away from each other. Technically, away from the protons. you're got them trapped in some position where they're loosely bound to either one. They've balanced the charge between the two, essentially, the electron probably has, and neutralized this strong bond into a weak bond. I guess that would be the way to say it. So if something's sticking to if there's two surfaces and one of them's charged, it can be thought of kind of simply as, so there was two surfaces that have protons in them, and those protons can collect more electrons than they have. So protons can always attract more. So if there's an electron here, an electron here, an electron here, an electron here, this proton can hold more electrons than it has. So they can cover all their proton can radiate shadow in all these directions. So it can collect quite a few electrons technically. The only thing limiting how many electrons are in an orbit around a proton is the repulsion between the electrons. They won't allow them to get any closer. That's why they have to go further out, is because to have more, they need more space, because they have to maintain this distance from each other. So anyway, so as the two objects are coming towards each other, let's say one of them's positive charge, so it doesn't matter which one. Let's say negatively charged, because we're saying an extra electron. So it doesn't matter which one I have it on, right? And as I bring the thing towards this thing that has less electrons. So this thing is negatively charged. It has more electrons, and it's moving towards a surface that's the neutral state. That is, not that it has no electrons, it just has, you can just think of it as being more free. There's more space here than there is here. And so what's going to happen is the two get closer and closer, this electron's going to move to the position of balance between the two. So this strong force, essentially, is going to become much weaker because it's going to get stretched out. And so that's why it's a weak bond, because it's neutralized into an average between the two charges. Yeah, that's probably a good way to say it. A good enough way to say it. So if one was very positively charged and one was very negatively charged, then you could end up with still a pretty strong bond, an electrostatic bond, but you'd need a very large difference between the charges, and one would have to be the opposite charge for this not to be neutralized to some kind of compromise with a ground state or the average state. So yeah, so charge is just a surface thing. So the atoms have their own, the bound electrons, and then they have these free electrons. And the key with like conductors is they have lots of these free electrons, but I think more importantly the free electrons are very free, in the sense that they will migrate any extra pressure and balance it very quickly, instantaneously, very quickly. They'll take any charge, and if there's too many electrons in one spot, they'll move the charge to another spot. Where an insulator, the charge kind of is what it is. I mean, you can get it to move on the surface a little bit, but it kind of stays where you put it. Depending on the material, it stays. Like glass, apparently, it can be very difficult. You can put a charge on glass, but it can be really hard to get the charge back off again, because you have to unstick the electrons, and they're not very free. Let's put it that way. The free electrons aren't very free. So a conductor has loose free electrons, but highly rigidly bound atomic electrons. So the atomic electrons are almost impossible to break free from the proton, and the free ones are very free. And then an insulator would be exactly the kind of opposite, where the native electrons aren't very strongly bound, so force doesn't communicate through them very easily, and the loose electrons aren't quite as loose. Something like that. So what you're really just moving is the monopole. So static electricity really has to, so the word charge, when you hear that word, what I'm going to do in my brain now is think you're moving the monopoles, you're moving the magnetism, the magnetite, whatever you want to call it, the thing that creates magnetism, you're moving to the other place. And depending on how it's distributed, it'll either become magnetic or not. How it's distributed. Yeah, it's close enough. Yeah, so it's the actual pieces that make magnetism rather than the pieces in between the electrons that are creating the pressure. So in a conductor, it's really just about what side has the more pressure. So the negative side always has the more pressure, so it's backwards to what, the intuitive thing. And so if you have a conductor, whatever side starts out with more pressure, clearly as the pressure moves down the wire, it's going to be neutralized by the lack of pressure at the other end. So the other end has a lack of pressure. So it's like the two will kind of blend into each other. So this is strong at the end and gets weaker, and this is strong. The lack is strong, and then it gets weaker, and so it's sort of, the magnet is really just created by the starting electricity. So the pressure you start with creates your poles in the conductor, in the sense that this side is always going to be electron heavy because this side is pumping EMF, the force, and to pump the force you have to move a few electrons to do it. So essentially when the electrons are in a position and you create more pressure between this one by moving one, encroaching, so this one moves to this position, creating higher pressure. That pressure has to expand into this one, and then this one expands into that one. So it's really moving the electrons essentially. But the electrons aren't the force. Right. Yeah. Okay, so alright, so this conductor, just a straight conductor is easy to figure out because you can figure out where there's too much pressure and where there's too little pressure fairly easily. But it still holds true for, like, even if you have a coil of wire, what you're really doing, again, is just the same thing. You're going to end up with one half of the coil is going to be, the positive end. One end is going to be the negative end. But you're still going to have that middle point where you start converting from a too high a pressure into a too low a pressure, in terms of converting it into a neutral state, attempting to. A neutral state you can never get to as long as the power supply keeps pumping more electrons and it keeps pulling more from the other end. So as long as it keeps pulling from one end and pushing from the other end, it's going to be a continuous field created, a static magnet. And a static magnet can, if you use it with like if you put a piece of steel inside of a nail, then the nail will become a magnet. So you stick a nail inside of there, steel, you'll just convert it, it will create the same field in the magnet, the same unevenness. No, it will orient the domains to the field energy. So they'll be forced to align with the magnetic, the filtered quanta will force the steel to become also a filter and a magnet. Alright, by rearranging the domain. So again, it's this. So the argument about how that takes place, I was thinking about like how, grass or something, and how you blow a wind over it and the grass all goes down, changes its angle. And in a sense, when the grass is just waving in the wind, just breezes, it's randomized. But if a good wind comes, it all lines up in the same direction, sort of. And I think a similar thing happens with current. Current forces an alignment. So as long as the current exists, the electrical current of the flow of the force, the pressure will keep things from randomizing. So what else did I want to? I mean, I should add more than this. I hadn't gotten much further than that. It was just this idea about what, understanding that what creates the attraction in static electricity is more of a relationship between electrons than it is the force or the filtered quanta. It's more about the bond of the electrons to the material objects, where, like I say, you're sort of fooled with a magnet. As a magnet, the electrons can't be peeled off. They're part of the substance. So there's no question about peeling, sharing electrons. You can't share electrons with a magnet. So that's the difference. You can't just peel the magnetism off. And so the difference between static attraction and repulsion and magnetic attraction and repulsion is, in static repulsion, the weakest link is the bond of the electron to the atoms. And in a magnet, the weakest link is obviously the force, because you're not going to break the bonds of the atoms. Probably the way to, that was the revelation. Okay, so that's why I made the video. I'm hoping it would lead to some other brilliant insight, but I don't know if there is one yet. Still trying to figure out, like I said, it seems kind of obvious that it has to do with just compression, that a magnet creates compression of the electrons, then you're off to the races in terms of that compression moves the protons. And so you're just basically aligning the domains, which is creating the magnetism and facilitating the current. Now, why does it facilitate the current? I think just has to do with the fact that the electrons are closer together because of the compression. So it would seem logical that the force between them would travel more efficiently if, between the proton and the electron, which I think the current has to travel. But anyway, it would travel more efficiently if everything's more compressed. But, no. That's too vague. So I have to work on that. So I don't know if it's worth reading the second comment. I guess I'll read it and then I'll just say, oh, no, not ready for that one yet. Yeah, like I said, I was kind of hoping I would. I'm just, last couple of days just been brain tired. So that just might be part of it. I'm just not terribly inspired or motivated. I'm just trying to get myself focused. Alright, so at 3932, you said that moving the coil over the pole of the magnet won't get you anywhere. Well, I don't think I said that, but whatever, we'll see. But then you switched your answer saying that it could give you an AC current. Yes, movement is obviously movement is, like you could say, pressurized, unpressurized. So obviously if it's pressurized, okay, that's an action. And that induces a current just because you move something. So when you compress the electrons, you do actually move them, which means the force bits are compressed and then they're going to be pushed along the chain. Like I said, they're going to push the electron next to it, push the electron next to it, and one of those electrons has more stuff in between it now, and that's going to be basically your EMF. So you create a little bit of current when you push them and pressurize them. Now if you leave them pressurized, you're not going to create any more current because they're not moving. You've stuck them in a position. So the electrons have to be moving for you to sustain a current. So obviously if you move the magnet, then the electrons will bounce back up, and then you can push them again. So you can you can squeeze and unsqueeze the electrons, and the force between them is the thing that's going to squeeze out the end, so to speak. That's going to be your EMF, with a couple of electrons thrown in. But I'm just saying it's the force bits are the things that are going to get pushed out over the edge, and then it's always you got to pull something back in from somewhere else. So it just depends on how your battery's configured. So alternating current is just kind of squeezing it this way, then squeezing it that way, then squeezing it this way. Windshield wipers or something. So you're pulling back the same stuff you push to the other end. You end up pushing it back the other way. But yeah, so you have to compress something to squeeze the force out of it. That's an interesting way to say it. And so you have to let it relax again before you can squeeze force again. Alright, saying that it could give you AC current. Sure, but that seems like an ambiguous answer. True enough. Even what I just said is sort of ambiguous, but like I said, it's sort of like the wheat argument. You push it down, you could kind of see that the wheat at the end pushes down. So it creates an effect into the world, into the end of the wire. And if the wire is connected, then it's going to affect the wire and go back to the other end, kind of thing. So it's whatever you do, it's like a bunch of people in one of those human centipede things. If you made a human centipede into a circle, if you squeeze one of the humans, then his guts go into all the other guts and come back again. Almost, Alright. That's a great analogy, Gary. Anyway, I think it's worth pressing on the issue, but I won't press beyond this comment. Okay. Alright, so yeah, I might as well read this and see where it goes. 1. Imagine a magnet with a north side facing up. Now let's say I shake the coil left and right repeatedly on top of the north side. What happens to the current? Well, you get an AC current. Does nothing happen? Does AC current happen? Or does something else happen? No. So anytime you move something in a magnetic field, you're moving the wheat. And every time you move the wheat, you're going to get a current depending on which way you move the wheat. Same magnet, but now instead of moving the coil right and left, let's say I stretch the coil in both directions. Well, stretching, it's the same thing as moving it, so it's going to be perceived by the electrons as movement. Let me think. Well, not if you're already in the field. So no, if it's inside of a magnetic field, and you make the coil. See, you can't make the coil bigger. You can only change its shape. If you get my drift. Once the wire's coiled, you can't make the coil itself bigger and have the same number of windings. So that can't change. So all you're saying is you're going to take the same amount of stuff in a field that's static, and you're going to stretch it. Well, stretching it won't do anything, but the catch is, in stretching it, you're going to move it, right? I'm just trying to think whether you're going to move it across the field. So if it's just the north side of the magnet, I would guess it can't matter, because you have to go in and out of the field. If you're on the north side and you just shake it inside, like I said, if the magnet's bigger than your coil and you're shaking it, you won't get anywhere. Because once you're inside, it's all done giving a shit. You're not creating eddy currents anymore. Nothing's getting created inside the conductor. So the game's sort of over if your magnet's bigger than your coil. But if your magnet's smaller, well then yes, you're going to be changing what part of the field is getting relaxed or compressed. So you'll create a current. So you have to kind of describe the experiment a little more. You have to clarify whether your coil is inside the magnetic field or whether the magnetic field is a small field and you're just moving a coil over a small magnetic field. Alright, same magnet, both directions. What happens to the current when I'm stretching the coil? Is there nothing or is there clockwise current? Well, the direction, you know, I'm not going to commit to the notion of current direction beyond voltage, but whatever. Same image. So we did an image. Oh, okay, well, we'll go take a look at the image. Same image as something else before, probably. Okay, so it is a smaller magnetic field, apparently, from this drawing. So any movement of this coil is going to get you in trouble. So anytime you move it, you're going to be... See, moving this way, stretching it this way, okay, that's not going to get you anywhere. Because you're not moving this or this into the field, and this are in the same pressure. You're still in the north side or the south side. So if you stretched it this way, it would matter more because then you're changing. It still wouldn't matter much. If you get anything, it's going to be incredibly weak. I mean, obviously the north and south poles are stronger here, so it's a stronger magnetic field. So you're going to get something, but you're just getting the difference in the strength of the magnetic field. So it really depends on how strong the magnet is. If the magnet's very strong, then that difference will make a difference. If it's just a little bar magnet, that difference probably isn't going to be enough difference to notice. Okay, yeah, good answer, Gary, I think. Anyway, so conditional, yes, it creates something, but it's very, very small change. Alright, in the first question, you move the coil right and left. In the second question, you can see that it is, I stretch the coil. Yeah, well the catch is, if it's a strong magnet, I say stretching the coil will create a current. If it's a weak magnet, stretching the coil won't do anything. So, that's my stipulation to my conditional as an answer to your question. Yes. So this probably does get too complicated for some people. I mean, I should just make a list of all the things, because you have the heat issue. You know, and the relationship between heat and the destruction of both current and magnetism. So heat creates resistance in the conductor, makes it capable of conducting less electricity, moving less, and it does the same to the magnetism. It degrades it, and those are probably proportional relationships. So the real mechanism is figuring out the exact. So the other thing to think of with the static electricity I was thinking of is that you have to think that most objects have a charge relative to the ground, because that's the most things are connected to the ground, and they've collected the same amount of pressure as the ground has. The electrons in the ground connect with the electrons of the object whenever this thing touches ground, and all the electrons balance their pressure, the pressure between them, and equalize it. And so you have to take something separate from ground, some way that's separate, put in a separate place, put charge on it, extra electrons, and they can't be allowed to seep into ground. And then you can put quite a lot of charge on, depending on how much the atmosphere is going to leak the charge. So then the only issue becomes is how conductive is the air, how moist is it. And so that's the breakdown voltage, which is whatever it is, 3 million volts per meter. Um, and it seems like an awful lot. But anyway, um, 3 million volts at a meter. Yeah, that would make sense. It gets down to about 10,000 volts for a centimeter or something like that. That probably works out right. Oh, anyway, sorry, just my own wheel turning. So charge is just it's just a surface phenomenon in most cases. It's not like this battery. You can't charge isn't this the charge you're putting in the battery is a lot different because that's a whole chemical thing that's going on. It's not just surface electrons. So you're collecting the force in those circular traps where surface charge is just surface charge. It's just between the electrons on the surface. It doesn't go any deeper than that. That's why static charges are really weak in terms of their high voltage, low amperage. They just don't have any volume. They use them up really quick. The difference is kind of extreme, but the difference is erased really quickly. It doesn't have any depth, where a battery can hold a deep amount of imbalance and keep pumping it out. That might be useful to some of this, but all right. There's no point in. I won't hurt you any further. It is a little. Like I said, I haven't quite got enough of a model for the movement part. But I'm just saying the theory's all there, so you can really understand the theoretical part. And so I don't know if I want to get too deep into details of chemistry and molecular configurations to point out how they're creating magnets and all that kind of stuff. But again, the magnetism is more of a phenomenon of how the tons leave. So the last thing they go through kind of defines the identity through the mechanism, And so it's really, you can paint magnetism on surfaces, which is essentially kind of what charge is doing. But it's a very thin magnetism. Doesn't have any depth. Durability is maybe the word to use. Alright, well, that's probably, I don't want to torture it. I'm just trying to think if there's any other subjects to throw a little 10 cents in on. I did see a video on these jets that they're in the radio spectrum, so you see them with radio telescopes. And they apparently shoot out of galaxies. And they produce this radio noise, but they're made out of electrons and protons. And they're releasing the radio waves as they kind of decay. They're going very high speeds, high velocity. And it's apparently a very high amount of energy, and they're speculating it's coming out of the black hole in the middle of the galaxy or something that's shooting this stuff out. But the interesting thing is when you saw the size of it, so the galaxy would be like this size, and its stuff is jetting out of this middle portion into these two big plumes that sort of form, and they sort of round, as they finally run out of energy. And the interesting thing is it sort of looks like the range of many of these lensed images is right on that periphery, right at the same kind of distance that you see a lot of lensed images at. And so that would be another reason to speculate about the possibility of it being created by diffraction, not gravity. Just throwing that out there because it was interesting that those plumes of high energy particles create a bigger circle, a bigger arc than the arc of the galaxy. So it could fool you into making you think the galaxy was in a bigger circle, but it's really just the arcs of those plumes. So yeah, something to ponder, I think, worthy of a ponder. So these are things you can't see optically. You can only see as radio waves. The only signature these plumes leave that we can see are the radio waves produced. So that's sort of interesting. But they might not last very long. So again, it would be another thing where they could create lensing and then go away because the discharge of this energy is only temporary. Yeah. So doesn't. I mean, I'm still skeptical of the whole heavy masses in the middle of the galaxy thing. But my whole point about galaxies is that they are something falling apart, whether it's a black hole or just black matter, which I think is probably a better description of what could be out there. It's just a very big planet, of dense stuff, and compressing under its own weight, it explodes. It breaks down, and it does it in these different stages that create different manifestations of the breakdown. One manifestation is the creation of the spiral arms. The other manifestation is the release of these jets of electrons and protons. Anyway, interesting, I thought. Maybe, possibly. So anyway, till next time, and such. I don't think so. I mean, the guy's bringing up a stupid beer can homo motor, and I already said it. I mean, there's 3 magnetic fields being created. 4. There's the magnets and the shell of the battery, which becomes part of the magnet. So that's the one magnetic field. The current going through the battery, that's a second magnetic field. And then both of those create 2 different magnetic fields in the beer can. So you got 4 magnetic fields. I mean, that should be enough reason to say, yeah, there could be a possibility that that could turn into a motor, theoretically, because one field is forming and creating a hostile magnetic field, and then if that moves to get out of the way, the other field is also creating one that's hostile, and that moves. You can sort of get the idea that they end up forcing the recreation of that hostile field. Yeah, something like that. Alright, anyway, that's probably enough now.